For the next little video in the stats course, we're going to look at the way in which we use a normal distribution, a particular normal distribution. It's called standard normal distribution because it's a distribution of standard scores. And we're going to look to see how we use that normal distribution, that special standard normal distribution, to sort of set the template for the logic that we'll use for almost all linear statistical analysis. And you notice I said linear there. Well, we'll not go much beyond linear analysis because you know there are most of what we do in stats today involves some assumptions related to linearity, and so we will stick within that boundary so that we can get a little bit better explanation. But we're going to start looking at the standard normal distribution. We're going to talk about how it allows us to set up a model that we then can use as part of our process for developing other particular statistics related to different kinds of data. And so I'm going to go over to a screen share here. Excuse me, allergies, and see if we can you know, make a little sense out of this. The first thing we have to do is understand what a standard score is and generate standard scores. And one of the things that we need to generate standard scores is something called standard deviation. Well, a standard deviation is one of the many unbiased estimators that we use in statistics to help us understand what would be the expected distribution of random occurring events. And in order to calculate standard scores, we take the difference between a particular value and the mean of the group that value is from, and we divide that result by what's called standard deviation. Now, that generates for us what are called z-scores. And so here we have a set of scores, 5 scores, with a mean of 12 and a standard deviation of 5.52. Don't worry, we will not have to figure out how to calculate that. That'll be a descriptive statistic we'll look at a little bit later in the next video when we talk about the working with JASP to generate some descriptive information. And so, you know, a value of 18, a raw value of 18, subtract the mean is 12, so it gives us a value of 6. Divide by a standard deviation of 5.52, and we get a value of 1.09. Now, if we go down the other way and we take the lowest quantity here, 6, you know, subtract 12 is minus 6, divided by 5.52 is minus 109. Now, you begin to see some of the inherent nature of standard scores now, in that they are clustered around a mean value of 0, which represents the mean of the sample or the mean of the population, primarily the mean of the sample. And you see that they are somewhat symmetrical. Now, they won't be perfectly symmetrical because, you know, not all distributions are as contrived as this one is. However, they will be symmetrical. And so you'll have, if you added up all the values above 0 and subtracted all the values below 0, you would get back to 0 again. So it is a symmetrical outcome. And z-scores have these interesting properties. And one of those properties is that when we distribute a random occurring set of z-scores from a group, from a sample, and as we begin to add more and more and more elements to that sample and we get more and more z-scores, we discover that it becomes this very symmetrical standard, what we call standard normal distribution or distribution of z-scores. The legend at the bottom represents 1 standard deviation unit. So we start at the mean with 0, we go up 1 standard deviation unit, up 2 standard deviation units, up 3, so forth and so on. We go down -1, -2, -3, so forth and so on. Now, theoretically, this curve never meets the index line, never meets the axis. But beyond about 3 standard deviations, the values become so small they're relatively meaningless. And so most of what we want to know about the standard normal distribution lies between 3 standard deviation units above the mean and -3 below the mean, or 3z above the mean down to -3z below the mean. And so these units are described by standard deviation quantities and raw values. Now, under this curve, because it is perfectly symmetrical, we can not only anticipate, but we can know how many cases or how much area there is under the curve. And so we know that between 0 and 1 is about 34% of the cases, or 34% of the area. Between 1 and 2 is about 13.5% of the area. And so adding 1 and 2, or -1 and -2, we find that about 47.5% are between 0 and -2. Another 47.5% are between 0 and +2. The mean is 0, as I mentioned earlier, and the standard deviation unit is a z-score now, 1z. And so area within 1 z-score of the mean is about 68%. Area within 2 z-scores of the mean is roughly 95%. Now this becomes very important, because as we talk about what is statistically different, statistically significant from a group, or is the difference between 2 groups significantly different? As we begin to talk about significance, we begin to talk about probabilities. And so the probability of a value lying within 2 standard deviation groups of the mean is about 95%. The probability of a value lying outside of that middle 4 standard deviation units, 2 positive, 2 negatives, then would be about 5%. And so there would have 5% spread over these 2 tails if we were actually what we're doing called a 2-tailed analysis, where we're not interested whether one value is larger than the other. We just want to know if a value is different from the group, from the sample. And so we can say with 95% surety that the value probably will lie in between these 2 boundaries. These are called critical values. And we can also be about 5% sure, or 5% possibility of the value lying outside these boundaries. We call this the area of, call it a lot of things, but I just call it the area of, commonality, because we would say that these things in here, this 95%, are not statistically different from each other, or not significantly different from each other, any 2 values in here. We would say that a value out here, or a value down here, outside of that 2 standard deviation and -2 standard deviation range, would be significantly different from the group, because there would be a less than 5% chance of that value occurring purely by chance. And that's what we define as significance. Less than a 5% chance of that particular value, whatever the statistic is, whatever the statistical value is, lying more than 2 units away from the mean. And so when you say significance, we mean less than a 5% chance of that value being that far away from this area, this common area in here, in which all these things are considered to be relatively within the range of random error. Now, we put some real values with this just to show, you know, if we have a z-score of 0, and let's say we have some scoring or some scale or something, and we have a set of outcomes, and the mean of that on that set of outcomes of that sample is 75, standard deviation is 10. Well, at a 0 z-score at the mean, at this point right here, at the 0 z-score, that would be what we would call the 50th percentile. 50% of the area would lie above that value, 50% would lie below that value since it's symmetrical, and we'd say that would be the 50th percentile. And that would represent a value of 75, a raw value of 75 at the mean. Let's say we go up 1 standard deviation, which would be right here, 1 standard deviation. That would represent the 84th percentile. Why? Because it would be the 50th percentile below the mean plus 34% more area for the 84th percentile. And likely, when you go up to 2 standard deviations, it would be 84 plus 13.5. So this would be roughly the 97.5 percentile. If you go down 1 unit from the 50th percentile minus 34%, this would be the 16th percentile. And if you go down another unit, 16th minus 13.5, this would be the 2.5, 2.5 percentile. So you have the 2.5 percentile all the way up to the 97.5 percentile, 95% of the area in this middle. So anything that would lie within those boundaries of -2 to 2, in this case, raw score of 55 to 95, we would not consider to be significantly different from each other. A score of 97, we would consider to be significantly higher than the group. A score of 50, we would consider to be significantly lower than the group. And so we're using what we know about this distribution model to understand the likelihood of a particular value occurring. Now, as it turns out, this standard normal distribution occurs 2 places: when we're doing z-scores and when we have a set of values that has an infinite number of items. So this occurs when we have z-scores, and it also occurs at infinity. So at infinity, all these distributions will look the same. So no matter what the particular statistic is, and as we go through the statistics, you'll see that they look different. Different distributions look a little bit different. But at infinity, at an infinite number of items in a set, they would all look identical, and they would all look like a standard normal distribution. And so as we go from standard normal distribution up to infinity, which we'll never get to, the distributions for various other statistics would begin to take on the shape of a standard normal distribution, but only really get there at roughly at infinity. But the logic here is that we can know what that distribution looks like whether it's a standard normal distribution or whether it's some other statistic, we can know what critical values are, in this case, -2 and 2. In the social sciences, sometimes we call it the rule of twos. If you have a value that's 2 standard deviations above the mean versus a value that's 2 standard deviations below the mean, we would say anything outside of that is a significant difference. And so this idea of looking at the 95th percentile and the fact that it coincides with 2 standard deviation units almost precisely, not quite, we've rounded just a touch here, that it almost coincides with 2 standard deviation units means that there is some consistency in that thought process of saying, okay, how do we convert a z-score to a raw score to a percentile value? And all we have to do is we have to know the means of a group or a sample and the standard deviation. That model of logic we will use all the way through. We'll just be using different estimates of unbiased estimates, and we'll just be looking at slightly different distributions, but there will always be a critical value. And anything beyond that critical value will be significant. Anything less than that critical value will not be. So we're interested in those things that are unlikely to occur purely by chance. And that's how we define significance, is something that's unlikely to occur purely by chance. This 95% in here is a matter of occurring pretty much by chance. So that's how we use a standard normal distribution and this idea of z-scores to provide a logic set that we'll later use to talk about how we identify significance using just different statistical concepts and different statistical outcomes. And we're always, always, always interested in error, the difference between what we would expect to be random error, that would be this 95% here, and what would be either systemic or biased error, which would be out here someplace. All right. Next time we will begin looking at JASP a little bit, and we'll do some descriptive analysis using the JASP software program and talk through some of these values and some of this concept about standard normal just a little bit better. So have a good afternoon or a good evening, and I'll see you soon back on another video.